Maybe then I'll just start from the beginning again, yeah? So I'll just skip the overview part because that's something which you already know if you attended the last two lectures. Let's start from from this part. Huh? So let's now focus on the properties of the fluids in a confined fluid. And let's start with a simple situation where you basically have a fluid which is in contact with only one surface, okay? So that's the simplest situation. Earlier, what we learned were the properties which happens in a bulk. And now we just have the fluid and we are putting one surface next to it, okay? And the question is, how does the presence of this surface, or so to say the surface effects, going to affect the static and dynamic quantities which you are going to look at? So like we know, like we saw before, that when you have bulk, it's basically the bulk correlation length and the relaxation time which control the properties of the fluid, right? And we saw before that when the fluid is at the critical point of a second order phase transition, this bulk relaxation time basically diverges, and so does the bulk correlation length, right? And what I mean by the correlation length here is basically the correlation length which is related to the order parameter, right? And we saw before that if you have a single component fluid, the order parameter is nothing but the density difference between the liquid and the gas phases. If you have a binary fluid mixture, the order parameter is the difference in concentration of the A and B type of particles. And if you have a magnetic system, the order parameter is nothing but the magnetization, right? So now let's take this fluid and put it in contact with one surface. So let's have a look at this schematic picture. Here, basically, you have these fluid molecules, okay, and then we have this the blue surface. Now, one thing which you see very clearly, the presence of surface actually breaks the neighboring effect close to the surface. What I mean by that? Let's pick up one molecule in the bulk. And what I mean by bulk here is something which is quite far away from the surface. So for example, let's pick up this red molecule, okay? And as you can see, it has neighbors from all sides, right? So basically this red molecule is going to have interaction with all other molecules. And it has interactions from molecules which are existing in all directions, yeah? Whereas if you now pick up one molecule which is next to the surface, for example, say this yellow molecule, it has the neighbors on the right-hand side, right? But it doesn't have any on the left-hand side. Yeah. So clearly, the net interaction which this yellow molecule is going to face is going to be different from the one from the red molecule. So the presence of surface has now made a huge effect on the net interaction that the molecules are going to face close to the surface. So this is something which is known as the missing neighbor effect in the literature. Now, another thing which you can see from here very clearly, as you move further and further away from the surface, this missing neighbor effect, its effect is going to be lesser and lesser. So basically the surface effect, how much is it going to affect the properties? That depends on the distance from the surface. Yeah. Now, it can affect in two different ways. One thing is, of course, the missing neighbor effect, which I explained to you now. The other one is basically in terms of the strength of the surface interaction. So the surface molecule, the blue surface, this is going to have an interaction potential, or say an interaction with the molecules of the fluid, right? And it attracts or repels the molecules of the fluid with a certain strength, which is called the surface strength. And this surface strength, now, if the distance of the molecule from the surface is larger, even for the same surface strength, remember the net interaction that the molecule is going to face is going to be much lower if the distance from the surface is going to be larger, right? So the closer it is to the surface, the effect is going to be much stronger. Yeah. So the properties of this fluid is now going to depend on the distance from the surface as well. And this distance from the surface, we're actually going to denote it by Z, yeah, Z. So it's basically in the direction which is perpendicular to the surface. All right, so what are the other quantities the properties of the fluid are now going to affect on? We have already seen that it's going to be affected by the missing neighbor effect. It's going to be affected by the distance from the surface. It's going to be affected by the strength of the surface interaction, yeah. Now, that's what I mean here, that it's going to depend on the surface properties. What do we mean by surface properties? Well, one thing is, of course, the surface strength. The next thing is which of the molecules of the fluid the surface is going to prefer. So typically, if you look at real fluids, yeah, I mean, for example, the fluids which you actually see in real nature, yeah, not just the, the mathematical modeling, but if you look at the real fluids, typically they happen to have the surfaces, typically they happen to have a preferential attraction to one of the components of the fluid. So you can take a fluid which is a binary liquid mixture, which has two types of particles, like say oil and water. You can have a fluid which is even multi-particle. It can have 3 phases or 4 phases. And usually what is seen is that these surfaces, which you put into contact with the fluid, they usually have a preferential attraction to one of those phases, which means that, say, this surface, if it now favors the oil type of particles, clearly the oil type of particles from the fluid will try to go closer to the surface. It will get attracted more and it will try to form a layer of those oil molecules on top of the surface. So that's what I mean by the surface properties. Yeah. So which of the phases of the fluid the surface actually prefers? Now, you might have a situation where the surface is actually neutral, which is very interesting, by the way, where it doesn't really have any kind of preference to one of the two phases. But usually, if you look at real systems, it usually happens to have a preferential attraction to one of the two phases. So, and that's the kind of surfaces which we will deal with in the lecture today. Okay. Now, the other parameter that the properties are going to depend on is going to be temperature, right? Because remember, this fluid is going to be close to a second order phase transition. And like we saw that if you are closer to the critical point, the relaxation time diverges, the fluctuations in the system become very large. At the critical point, the correlation length, which is a measure of the length scale over which this fluctuation exists, that diverges. You have the strength of fluctuations, which is dictated by the susceptibility, which we saw yesterday, that diverges, right? So a lot of things are happening when you are close to at the critical point. So clearly, the temperature of the fluid is going to affect the surface properties hugely. Yeah. Okay, so that's what is depicted here in this mathematical expression. So now let's consider the order parameter. Okay, so let's say that the order parameter is denoted by it's psi. Yeah, it's denoted by the symbol psi. So what are the different variables that is going to depend on? It's going to depend on the perpendicular distance from the surface, which is z. It's going to depend on temperature, and it's going to depend on the surface strength, which I denote by h. Now, close to the critical point, like I told you, it's the distance from the critical temperature, which is important. And in certain conditions, so there basically, you can replace the temperature T by the new variable bulk correlation length. So this bulk correlation length will automatically take care of the temperature of the fluid as well as the critical temperature, the distance of the fluid from its critical temperature. And that is something which is extremely important when you have a fluid which is close to a second order phase transition. All right. So these are some of the properties of a fluid which is in contact with one surface. Yeah. And the surface properties, like you see, it's going to enter in terms of H. Okay. And yeah, like I hope you have already seen when I was explaining the missing neighbor effect, that the moment you have a surface, the translational symmetry of the system is going to get broken, right? And what do I mean by translational symmetry? Like, I mean, I'm sure you have already learned it in the textbook during your MSc and BSc courses. So basically you translate a molecule by a certain distance d and the properties are not going to get affected by that translation, right? So I leave you as a homework to you to find out that when you have translational symmetry in the system, which quantities are going to be conserved. Yeah. So that will also give you an idea about when you have a confined fluid, where because of the presence of a surface, you no longer have translational symmetry. So which quantities are no longer going to be conserved in a confined fluid as opposed to a bulk fluid. Okay. So this I leave up to you to find it out as a homework. Okay, so now that we have learned what's going to happen for one surface, let's now try to find out what will happen if I have two surfaces. Okay, so before I have only one surface which was in contact with the fluid. Now let's put the fluid in between two surfaces. Namely, what I mean here in the schematic picture, basically that you have this pink walls. So those are basically two walls, which are two parallel walls. And then you have the fluid in between. And the fluid is basically marked by this blue part here. Yep. And this kind of configuration is also called a slit geometry. Okay, so that's a term which we will find very commonly in the literature, that you have a slit. What do we mean by the slit? It's basically two parallel walls. Okay, and these walls have selective surface adsorption properties, which means that both these walls will actually try to prefer one of the two components of the fluid. And for the simplest scenario, we are going to consider that, let's say, both the walls, they're going to prefer the A type of particles. Okay, so that's again called a symmetric wall. Now, suppose that instead of a symmetric wall, which means that both the walls are preferring A phases, if I have a situation where I'm going to say that, okay, let's say that the first wall will prefer A phase and the second wall will prefer B phase, that's called an antisymmetric wall or an antisymmetric slit. Okay. All right, so now let's try to have a look at what's going to happen to the quantities which you are going to now consider. So the psi here, just like before, it's going to depend on the distance from the wall. Z, this distance can be from any of the walls. Yeah, it's going to depend on the temperature. It's going to depend on the surface strains of the surfaces. And because you have two surfaces now, we have two variables, H1 and H2. In addition, very interestingly, one more new variable now becomes important. And can you guess what is that? It's basically the distance between the two walls. Okay, so this term D here, which depicts the distance between the two walls, that now becomes extremely important the moment you have a two-wall system. And why so? Remember, it's because when you have a fluid which is close to the critical point, you have fluctuations which are developing in the intermediate fluid, right? Which actually leads to the correlation length. Now, if I have a slit where both the walls are very far, separated by a far distance, clearly, any kind of perturbation, if I make it at the first wall, its effect is not going to reach the second wall, right? Because the distance between the two walls is so large that the effect of the first wall perturbations is not going to reach the second wall. On the other hand, if the two walls are very nearby, whatever changes or whatever fluctuations or perturbations you make at the first wall, it's going to affect the properties close to the second wall very strongly, right? And that's a situation what we call that when the two walls are very closely correlated with each other. So the distance between the two walls, D, now becomes extremely important for a confined fluid close to the critical temperature. So now let's try to do the finite size scaling for a two-wall system. So if you remember, yesterday I was already explaining to you the method of the finite size scaling, starting when you have finite size effect, how you can define certain scaling variables, and with that, how you can actually do a certain kind of scaling analysis. So we are going to follow the same procedure today as well. Let's try to find out, when you have a two-wall system, how does the property of the order parameter in between going to behave? Okay. So for that, let's start with the basic expression for the order parameter. It's critical singularity. We know that the psi, it actually shows a critical singularity at the critical behavior, at the critical temperature in terms of the reduced temperature epsilon with an exponent beta. Yeah? So this epsilon is actually T minus Tc by Tc. Okay. So it dictates how far you are from the critical temperature. Now, the question is, how am I going to define the order parameter now? Because remember earlier, all the order parameters that we were talking about, those are the situations in bulk, right? Now I have two walls and I have a fluid which is confined in between these two walls. So the question is, what's going to be the definition of the new order parameter? Can I take the same order parameter as before? Well, the answer to the question is clearly not. And why not? Because the moment you have two surfaces, the structure of the fluid in between, which you are going to see, it's going to depend on the distance from the surface, right? Like I told you before, if the surfaces prefer A components, I'm going to have a layer of A components on top of the surface. And in the middle of the slit, it's going to be the presence of both A and B type of particles. And so you're going to have some kind of layering structure. So if I look at the order parameter, it's now going to be distance dependent. So that's why I have to define a new order parameter now, which is a function of the distance from the wall, which is Z. And one way to define it is actually as the local difference between the number of A and B components, which is made dimensionless by the total number. So what was the definition of the order parameter in a bulk? It was simply capital NA minus capital NB, where capital N is the total number of A or B particles, right? So that's what was the order parameter in bulk. Now we are talking about a confined fluid. I'm looking at the same quantity. It's the difference between the A and B type of particles. But now, instead of the total value, it's the local value, okay? The value which depends on the space coordinate or on the distance from the wall, namely the small n and small b, which is a function of the distance z. Okay, so I hope that's clear. If you have any questions on this part, you can just put it on the chat box. Okay, so there are a few questions already. Sorry, I forgot to pick it up. When we use correlation length instead of temperature in psi, do we assume that psi behaves symmetrically around the critical temperature? Okay, it's a very good question. The answer to that is the psi doesn't depend on, it doesn't behave symmetrically or anything. What it does is that the psi just shows a singular behavior at the critical temperature. Okay, remember that this bulk, just 1 minute. So do you see the screen? Okay, yeah, so remember that this bulk order parameter, it has a non-zero value below the critical temperature, and at the critical temperature or above the critical temperature, it's basically 0, right? So the similar thing happens in case of a confined fluid as well. So whatever singularities you are going to observe, it's going to be below the critical temperature. Okay, it's going to approach 0 from before. Okay, let me just try to see if there are any other questions. All right, so since there are not, let's now get back to the slides. Okay, so this is going to be the new definition of the order parameter. Now let's try to incorporate the presence of the surfaces, and let's try to see how does the behavior of the surface going to affect the property. So let's have a look at this equation here. Okay, we know that the psi, it behaves as psi 0 times epsilon tau power beta. Yeah. Now I have replaced the psi by the new variable phi because of the presence of the surface, right? Because now the order parameter phi now depends on the distance from the wall, which is z, as well as temperature. And likewise, I can now write this phi is basically going to be equal to phi 0 times epsilon tau power times beta. So which is just like the similar kind of situation which was in bulk. But now because you have a surface, you are going to have a new scaling variable which is going to enter into this expression. And this scaling function is basically capital P. And that's a scaling function which depends on the scaling variable z over xi. So note that the scaling variable is once again dimensionless. It's a ratio of two length scales. So it's basically dimensionless. Yeah. And the fact that the phi, the order parameter, depends on distance and temperature is once again captured by the scaling function as well. How? The z simply enters as z, and the temperature enters in terms of the correlation length. Okay, so everything is basically consistent and matching with each other very nicely. So this is the expression of the order parameter, the local order parameter. when you have only one wall. Now, when you have two walls, what's going to happen to this expression now? So for that, let's have a look at this equation, which is in this parenthesis here. So like I mentioned before, now you see you have the two variables, Z and temperature. In addition, you now have the new variable, which is capital D. And capital D is the distance in between the two walls. Okay, so the phi 0 remains as phi 0 like before. How does the second term enter? Well, that's because you have this epsilon power beta, and the reduced temperature epsilon, you can now write it in terms of the bulk correlation length xi. Okay, and the xi is related to the amplitude xi 0, if you remember the notes from yesterday. And now it's going to depend on the distance between the two walls. So now this quantity is actually dimensionless. The ratio of d and xi 0, and this is now raised to the power minus beta over nu, just like the equation which is written above. How does the nu enter? The nu enters because now I have written the reduced temperature epsilon in terms of the correlation length. That's why the nu enters in the exponent. Okay. So now let's have a look at the scaling function. The scaling function has now become a function of two variables. Unlike the one above, which is a function of only one variable. Now we have two variables. So it namely depends on Z by D, which is once again dimensionless. And it also depends on D over xi. So the D over xi, this variable, captures the dependence on temperature. Now the point to note here is that both these scaling variables are dimensionless, and the new parameter, the new variable D, enters both the scaling variables. Okay, so this is the main concept of how does the property of the fluid, namely the order parameter, going to be affected when you have the presence of two surfaces. Okay, so now with that, let's try to have a look at some results. Basically, I'm going to show it to you results from computer simulations for a fluid, a binary liquid mixture, parameter on the y-axis, and the x-axis is basically the distance from the wall, okay, from the first wall. So this is once again a fluid which is confined in between two walls, okay, and z is the distance from the left wall. Different colors here correspond to different slit widths, and all the data correspond to the critical temperature Tc, okay. So what do you see here? First of all, you see that the value of the order parameter, it starts from a value which is almost close to 1 for all the system sizes. It doesn't really depend on the system size. Why so? Because all these results correspond to the same value of the surface strength. And since I have kept the surface strength the same, the value of the order parameter on top of the surface layer is more or less the same, no matter what is basically the prevalence of the A type of particles on the slit. And similarly, if you look at the value at z equal to 10, which corresponds to the other slit, the other wall of the slit, there once again, the order parameter is positive. So basically, both the walls are favoring A type of particles. That's why you have the order parameter profile. It starts from a positive value because it has the preference of A type of particles. It goes down and down. Finally, beyond a certain distance, it becomes negative. Why negative? Because remember, the total order parameter is 0. So for it to be 0, because the order parameter is positive, close to the two walls, it has to be negative in the middle. And finally, the point to note here is that it's a symmetric profile. Why symmetric? Because I have chosen the wall such way that the surface properties of both the walls are basically the same. So it's a symmetric wall, and that's why the profile is also going to be symmetric. So now this red data corresponds to the narrowest slit. Yeah. Let's now have a look at the blue data, which corresponds to the widest slit. Okay, so it's for the slit width equal to 30. So here, once again, the basic feature that you see is the same, right? So I have the walls here at z equal to 0 and z equal to 30. And on top of the surfaces, the order parameter values are more or less the same, once again, because it's a symmetric wall. And the order parameter is positive simply because it favors the A type of particles. And in the middle of the slit, I have the negative value. The total order parameter is 0. Now, what is the difference between the two cases? If I consider the slit d equal to 10 and d equal to 30, what is the striking difference that you observe here? It's clearly in terms of the distance at which the order parameter value becomes 0. So at the distance at which it crosses over from a positive value to the negative value. Yeah. And this distance marks, it depends on the correlation length of the system and on the surface affinity. Now, in this particular case, I have kept the surface strength the same. So it doesn't really depend on the surface strength that much. I have kept the temperature also same. What it depends on is basically the distance from the distance in between the two walls. Okay. And as you see here, as the distance between the two walls increases, the length scale at which the order parameter profile crosses over from positive to the negative, which basically marks the width of the surface adsorption layer, that increases as the slit width increases. So the moment you have a wider slit, there is more space for the A type of particles to come and form a surface adsorption layer on top of the surface. So the thickness of the surface adsorption layer now gets wider and wider the moment I increase the slit width. Okay. All right. So now let's have a look at the dependence on surface strength. Okay. So I hope you can already guess from here that the moment I have higher surface strength, it's going to attract the A type of particles more strongly. So if I then look at the order parameter value, which is basically the difference between the number of A particles and the number of B particles, locally, of course, the moment I have higher surface strength, this difference between A and B type of particles is going to be higher and higher, right? And that's what you see here. What I plot here is the order parameter on the surface as a function of the surface strength. And you see that as the surface strength increases, the order parameter on the surface also increases. Why? Simply because I have more number of A particles now, which are coming and sitting on top of the on the surfaces. Okay. And very interestingly, it also exhibits a power law dependence, and it does so with an exponent half. So there is a certain importance of this power law exponent half, which you see here. I will not get into the details. If you are interested, we can come back to it later, and then I can explain to you later. Okay. But nevertheless, for the time being, without getting into the details, just keep in mind that if I increase the surface strength, the value of the order parameter on the surface also increases. Okay. So now let's have a look at the dependence on temperature. Okay. So remember the earlier works that I showed you. Okay. So these results all correspond to the same temperature, T equal to Tc. These results all correspond to the same temperature, T equal to Tc. So I haven't changed the temperature of the system at all yet. Okay. Now in the next slide, which you are going to see, is how does the behavior depend on temperature of the fluid. Okay. So namely, this red data that you look at, that corresponds to the bulk critical temperature Tc, and the blue data corresponds to a temperature which is very far away from the critical temperature. It's a very high temperature, which is quite far away from the critical temperature. And you see the striking difference here. First of all, when you are at the critical temperature, the value of the order parameter on the surface layer is much higher. It's close to 1, whereas in case of the high temperature, it starts from a value close to 0.8. Okay, and why so? Well, that's because when you are at the critical temperature, the closer you are to the bulk critical temperature, the higher the value of the bulk correlation length. And that's going to affect the value on the surface layer. The next point to note here is that, once again, in terms of the thickness of the surface adsorption layer. So if you are at the critical temperature, the thickness of the surface adsorption layer is much, it's more thicker. As a result, it crosses over from a positive value to the negative value at a much higher, distance from the wall. And then you have the similar behavior close to the other wall, simply because it's a symmetric slit. Okay. Whereas if you look at the properties which are at a very high temperature, T equal to 5, first of all, the profile, the order parameter profile that you look at, it's almost flat for the wider region of the slit. Okay, so there is not much really happening in the middle of the slit if you are close to the, if you are at a very high temperature. All that is happening is that you have a surface adsorption layer here, another surface adsorption layer at the second wall, and at a the thickness of the surface adsorption layer is also pretty small. And then if you are like in the middle of the slit, it's almost like nothing is happening, it's more or less like flat. Whereas if I'm at the critical temperature, the thickness of the surface adsorption layer is much thicker. It crosses over and then it's flat only for a very short region in the middle of the slit. It's not really flat at all. In fact, one can do certain analytical calculations using mode coupling theory, etc., to show that the behavior of this order parameter profile is actually going to be parabolic. Okay, so the functional form is also going to change. Okay, and it does depend on the temperature of the system. Okay, so I hope I have already convinced you that the temperature of the system is actually a very important parameter in deciding the surface properties of the fluid. Now, remember, I told you before that you can do certain kind of scaling analysis, right? So this is the expression which I have already showed you before, and I told you how one arrives at this expression. Yeah, so this is basically the local order parameter phi, which depends on the distance from the wall, z, depends on the thickness of the slit, capital D, depends on the temperature. Yeah, and then one can relate it to a scaling function, capital P, where the scaling function has two variables. Both the variables are dimensionless. The first variable is z over d, and the second variable is d over xi. Through xi, the dependence on the temperature enter into the scaling function. So let's now try to see how we can plot this scaling function. Now the point to note here is that it's a function of two variables. Yeah. So how am I going to plot it? Well, one way to do that is, of course, you keep one variable as constant. So then it's going to depend on the other variable only. And that's what I'm going to look at. So in this picture here, what I plot is the scaling function, capital P, as a function of the first variable, z over d. And I have kept the second variable, d over xi, at a constant value. So all these results correspond to t equal to tc, which means that at tc, the bulk correlation length basically diverges, which means that the d over xi is basically tending to 0. Yeah. So the second variable now becomes used. I mean, it's a constant. It doesn't. We are not really need to worry about it. All we are concerned about is the behavior of capital P as a function of z over d, and that's what is shown here. So the different color here, different colors, they correspond to different slit widths. So I'm basically changing capital D here. Okay. Now, first of all, to note here. Okay. So I have the slits at z equal to 0, and the other slit, the other wall at z equal to d. Okay, so at 0 and 1 we have the walls. First of all, you see that when you are close to the walls, both at z equal to both at x-axis equal to 0 and equal to 1, the value of the y-axis is very different. Why is it so? Because when you are close to the walls, because of the surface effects, things are not really universal. Okay, so once again, the concept of universality comes into picture here. So you will have some features which strictly depend on the properties of the surface. Okay, so very close to the surface, the scaling behavior which you see here does not really hold. You need to be away from the surface by a certain distance, typically of the order of the molecular diameter. Only beyond that, you can observe the universal kind of features. Okay, and that's why you see that beyond a certain distance, data from different system sizes, they all now collapse on top of each other. What it means is that it's basically it's a very nice scaling behavior which you observe here. Yeah. So the data from different system sizes are now all falling on top of each other. So that's the data collapse which one expects to observe from this expression here. And the solid black curve line here, which you see, that marks the parabolic kind of behavior which I was talking about. Okay. So if you are in the middle of the slit, the behavior of this function, the behavior of the scaling function, it's actually quadratic in nature. Okay. So these are some of the properties of the static quantities. Let's now have a look at the dynamic quantities. Okay. So the dynamic quantities, once again, like the static quantities, they're going to depend on the surface properties. By surface properties, I mean that the surface strength, interaction strength, as well as whether it's going to prefer, the A type of particles or the B type of particles. The quantities are going to depend on the distance from the surface. They're going to depend on temperature. They're going to depend on the slit width. Now, in addition to that, for the dynamic quantities, one more thing becomes extremely important, and that is something which is known as hydrodynamics conservation. What do I mean by that is the following. When we mean hydrodynamics conservation, it basically refers to mass, momentum, and energy conservation. Okay. Now, if you have a solid, the only mechanism, the transport mechanism there is basically diffusion, right? The solid atoms of the molecules, they cannot really move much, right? It's pure diffusion mechanism that they can only vibrate. Whereas if you have a fluid, it's possible for the fluid molecules to actually undergo some kind of very advective kind of motion, and they can really flow under the effects of hydrodynamics. And that's what I mean by this hydrodynamics conservation. So if I'm going to look at the dynamics of a confined, if it's going to be a solid, the behavior is going to be very different than if we have a fluid. And in fluids, this hydrodynamics conservation becomes extremely important. Now, an important question here, say if I'm going to look at the properties on the surface layer, I'm going to look at the time-dependent properties. What is really tricky is the definition of the surface layer for fluids. Why so? Because remember, when you have a solid, it's all lattice structures, right? So I have very periodic structures, and the very first structure, the very first lattice point, that the first row, I can always consider it as the surface. That's where the surface is, and because it's periodic, it will give you the idea about the surface properties very easily. But the moment you have a fluid, these are basically continuum, it's basically a continuum dynamics, right? So the particles are not really lining up like on a straight line. It's not really a lattice structure any longer. So what you mean by the surface layer then becomes very tricky. And typically what one can do is to consider a thin layer, very thin layer close to the surface. And I'm going to say that, okay, fine, that layer I'm going to define as the surface layer. Okay. And that's what is defined here in this expression. Phi 0, what you are going to do is that you are going to basically integrate the local order parameter phi z between a certain, a small window close to the surface. And this window, the thickness of this window can actually affect the properties which you are going to look at. So remember, when you choose this window, you have to be very careful that it cannot be so small that you don't really have many more particles, surface particles close to the wall. At the same time, it cannot be very thick as well, that all the effects of the surfaces are already very, the effects of the surfaces are no longer there. So you have to choose it very carefully. Okay. Okay, so there is a question. Let me just take it before I move on. In slide 6, is the total number of particles A or B kept same for all the D values? Yeah, so for all the results, it's basically a symmetric binary liquid mixture, 50-50 binary liquid mixture, where we say that whatever be the total number of particles, 50% is going to be A particles and 50% B particles, okay? So it's the same. All right. So now let's look at the results for the transport quantities. So the question we are going to address is the following. We are going to look at the non-equilibrium dynamics of a binary liquid mixture, which is confined in between two walls. Both the walls prefer A type of particles. Both the walls have the same surface strength, which means it's a symmetric slit, okay? And what I'm going to do is that I'm going to say that initially the fluid which we consider is at a very high temperature above the bulk critical temperature. So that initially the fluid is very nicely homogeneously mixed. That's what I mean by initial T less than 0, it's homogeneous phase. Then at time T equal to 0, sorry, this will be small t, okay? So at time T equal to 0, now I quench the temperature of the fluid to the bulk critical temperature, okay? And the question is, what's going to be the non-equilibrium dynamics following this temperature quench? So for time T greater than 0, what's going to be the non-equilibrium dynamics of the fluid? And as you can guess from here, this dynamics is going to be affected by the surface properties of the confining walls. Yep. Okay, so the first thing that you are going to look at is how does the order parameter on the surface, what we denote by phi 0, how does that going to behave as a function of time after I have already done the temperature quench? Okay. And I show you here the data for that particular non-equilibrium, the quenching experiment, basically, for different system sizes. So basically say the red data and the yellow data. Okay, for example, let's just focus on the red data here. Okay, so that corresponds to the thickest, the widest slit with which you are going to consider. So let's focus on the red data first. First of all, what you see is the following. After I have done the temperature quench and the fluid is undergoing the non-equilibrium dynamics, the surface order parameter value, it starts from a very low value. It undergoes some kind of oscillation. It starts to increase. Why does it start to increase? Because remember, initially, I have a purely homogeneously mixed fluid. Okay? And the correlation length, the bulk correlation length was very small because it was at a very high temperature. Now, after I have quenched it, correlations are now developing in the fluid in between, right? Because now I have quenched it at the critical temperature. So at the critical temperature, you know that the bulk correlation length is actually very large. It's going to diverge in principle in the thermodynamic limit. So now after you have quenched it, you have certain correlated blobs which are forming in the fluid through which the correlation is now going to increase. More number of A particles are now going to come close to the surface. If you look at the order parameter value on the surface, it's going to increase now. And that's what is shown here. It starts from a low value, it starts to increase until or unless at very late time, it finally has saturated. Why does it saturate? Because finally then it just reaches the steady state, basically. But what's interesting is the intermediate region, where you see for a certain region, this order parameter, the surface order parameter, does exhibit a power law growth regime. And it does so with an exponent 1 over Zc. Zc is called the dynamic critical transport critical exponent, what it's associated with the relaxation time tau, which I was talking about before. So the initial regime, okay, so say starting from the early time t equal to 1, close to t equal to 100, this initial regime, it's again, it doesn't belong to any kind of scaling regime at all. The intermediate regime, say from 100 to 1000, that belongs to the scaling regime. Okay. So this early part here, that's like non-universal, it's going to be affected by the surface properties, whereas the power law scaling regime, that's like universal behavior. So no matter which fluid you consider, whatever going to be the surface strength or the surface width, it's going to exhibit this kind of power law behavior. Okay. Now, one thing to note here is that let's now consider compare this red data with the blue data. Okay, the blue data is for a very narrow slit, namely d equal to 20. One striking difference that you see here is that the moment you have a very narrow slit, this power law regime has almost disappeared. Why so? Because things are happening so fast and the two walls are now getting correlated so fast that you don't really have a wider time window beyond which you can characterize the power law growth regime with proper resolution. Okay, so when you have a larger slit width, you can actually then capture this power law growth regime very nicely. So this, you remember, it's the plot of the order parameter as a function of the time. And as we see at very late time, it has now already reached the steady state value. So the next question we are going to ask, how does it approach the steady state? This power law regime, it gives you the information about the early time behavior. Okay. Now let's get interested in the late time behavior. By late time, I mean the time which is going to be very close to the steady state kind of behavior. Okay. So namely, say from 100 to 1000, it's like the early time behavior. What's going to be the behavior beyond 1000? So beyond, say, 1000 to 20,000 or whatever, how it's going to be the behavior. So that's the late time behavior, which you're going to see. And for that, what we are going to plot now is basically the difference. So first of all, you look at its difference as in comparison to the this equilibrium value. All right. So first of all, what you see here is that it's going to decrease as expected, because it's going to, the difference between the time dependent value of the order parameter from the equilibrium value, it's going to get lower and lower as the time increases, because finally it's approaching the equilibrium value, right? Now, the point to note here is that if you look at the red data, which corresponds to a wide slit, it once again exhibits a power law behavior. So this is the double logarithmic plot. So I hope you know already that if you have a double logarithmic plot and if your data, it actually shows a straight line behavior, that means it's a power law behavior, right? Whereas if you have a semi-log plot and it shows the straight line behavior, that's an exponential. So yeah, if you don't know about those things, you can just, you know, check it today. Yeah, how do they come? So remember, double logarithmic straight line means it's power law. And if you have semi-log and it's straight line, means it's exponential. Just find it out why it's like that, okay? So let's come back to the red data. And what you see here is that it does exhibit a power law behavior with a certain exponent, which value is close to 0.67. But at the moment you have a narrow slit, so the yellow data and the blue data, they correspond to a narrow slit d equal to 20, and you clearly see that it's not a power law behavior at all. It's not a straight line. In fact, if you do the calculation, you will find out that it's actually exponential behavior that you observe for a narrow slit. And that is something very interesting, because now you see that the dynamics of the fluid, how wonderfully it depends on the slit width, how it depends on the distance between the two walls. If you have a very wide wall, it's going to exhibit a power law dependence. But the moment you have very narrow walls, when the walls are very close to each other, instead of a power law behavior, it exhibits an exponential behavior. Okay. And that has, it is a manifestation of the fact that the moment you have a very narrow slit, it's basically the finite size effects which are going to play a very crucial role. So it changes the behavior from power law to exponential suddenly. Okay. All right. The next thing we are going to consider, how does the critical fluctuations develop on the surface layer? So if I'm going to, after I have quenched the system, okay, so initially I had a very nicely homogeneously mixed system, and the order parameter fluctuation was, it was close to 0 because it was very high temperature. Then I have quenched the system to the critical temperature. So I have critical fluctuations developing, in the intermediate fluid. And the question is, how does the critical fluctuation develop on the surface layer? Yeah. And we characterize that in terms of the variance of the order parameter. Yeah, so it's delta. So I hope you know that. How is it related to the formula of this variance, right? So it's basically the square average minus the average square. And let's look at this quantity now as a function of time. But you see once again that it starts from a very low value, and that value is once again the equilibrium value at the initial temperature. It shoots up, it starts increasing initially. And why does it increase? Because after you have quenched the system, suddenly things have become, it has gone out of equilibrium. So it's the initial non-equilibrium effect which is going on, which is going to give a kick to the fluctuations. So things start increasing very rapidly. And then beyond a certain time, it starts to decrease, right? So that's the time basically when things again try to settle down in the fluid, in the intermediate fluid. And it takes some time, and then finally at a very late time, it once again reaches a plateau. And if you compare this time, this 10,000, to the plot which I showed you there, you can actually see that the time after which the fluctuations have now, like more or less reached a plateau, is the same time when if you look at the order parameter profile, that has also reached the plateau more or less. Okay. So this is how basically the non-equilibrium dynamics in the fluid is going on, that initially you have a fluid where the correlation is very low. You have no layering, nothing. You have a homogeneously mixed fluid in between the two walls. Then you have quenched the fluid. Now you have fluctuations developing in the system. You have critical fluctuating blobs which are developing. That's why if you look at this variance, it starts to increase. You have layers of A type of particles forming on top of the surface. That's why if you look at the value of the surface layer order parameter, it's increasing. And then finally, things are going to reach the new equilibrium state. Okay, so that's about the non-equilibrium dynamics which goes on. Okay, so I was planning to talk about something called critical Casimir effects, which is something which one observes when you have, in case of a confined fluid, once again. But before that, let me just ask. So Sudipta, are you here? So either I can stop the presentation now and we can answer some of the questions which we got yesterday. Either we can address those questions or I can go on with the slide. Okay, so let's then just continue. Yeah. So what is this critical Casimir forces? Okay, so critical Casimir force is basically a critical fluctuation induced force. And it acts when you have a confined fluid, which is very close, which is confined in between two surfaces. And the surfaces are very close to each other. So to understand why it happens, let's have a look at this schematic picture here. So this is once again the phase diagram of the same binary liquid mixture, which I explained to you multiple times before. So I'm not going to get into it again. You already know it. Let's consider the second schematic picture here. What it shows is that you have two walls, A and B, and you have a fluid in between. Okay, and say the blue wall, it prefers the A type of particles, and the red wall, it prefers the B type of particles. Okay, and we have already seen now, because of the surface effect, you will have a surface adsorption layer which forms on top of the surface. Yeah, so you will have a surface adsorption layer on top of the A part, on the wall A, the first wall, with a preference of the A type of particles. Okay, that's why the order parameter is positive here. On the second wall, you will have another surface adsorption layer, but this time the order parameter will be it will be negative because it prefers the B type of particles. Now, if these two walls are very much separated from each other, you will have the profiles just like independent walls. Okay, so the profile due to the first wall is not going to get affected by the second wall. However, if the distance between the two walls is pretty small, then the profile which is going to form close to the first wall, it's going to get affected by the presence of the second profile. And finally, you will have an effective profile, which I hope you can see here is marked by the yellow curved line here. So then basically you have the two walls which are correlated with each other, which are coupled with each other, and the two profiles have now become sort of, correlated, and you have an effective profile. And when you have a situation like this, that is the time basically you observe something called the critical Casimir effects. So what do I mean by that? Okay, so to understand that, let's have a look at the pressure. Okay, so I'm going to look at the pressure P, which is exerted on one of those two walls by the fluid in between. So say, for example, the second wall is not present at all. So I have just one wall and I have the fluid. So in such situation, the pressure which is going to, which is going to act on the first wall, it's basically nothing but the bulk pressure, right? The PB, bulk pressure, which depends on the temperature. Yeah. And why does it depend on the temperature? Because the interaction between these bulk molecules, that depends on the temperature. So the PB is a function of the temperature only. Now let's put the second wall. The moment I have a second wall, then the pressure on the first wall, it's going to depend on the presence of the second wall as well. So now it's going to be a function of two variables. It's going to depend on temperature as well as the slit with capital L. Yeah. In addition to that, it's also going to have a contribution from a third quantity, which is called capital PC. Namely, this term now depends on the separation distance between the two. So basically, this term is called the Casimir force. What it means is the following. If the L is very large, okay, which means that if the first wall doesn't really feel the presence of the second wall, the pressure that the first wall feels is basically the bulk pressure. However, the moment I have the second wall, and if the distance of the second wall from the first wall is pretty nearby, then the pressure that the first wall is going to feel is going to depend on the second wall as well. And in such situations, one can show that the total pressure which is exerted on the first wall can be written as a combination of two terms. So there are going to be contributions which are coming from two terms. They're going to be a bulk contribution, the PB. Bulk contribution is the one when you have no surface, no second surface at all. In addition, you are going to have a contribution PC, and this PC is called the Casimir contribution, the Casimir force, which is going to absorb the contributions due to the distance between the two walls as well as the surface effects. Okay, and you can once again do certain analytical calculations where you can show that this Casimir force PC has certain kind of singular behavior, etc., close to the critical point. Okay, so the concept of this critical Casimir force is actually a very important concept for confined fluids, and it's a highly active field of research at the moment, in the community all over the world. Yeah. So I'm going to end the discussion on the Casimir force with this slide here. What I wanted to show you is some interesting features that this Casimir force can exhibit. So like I was showing you different scaling behaviors in the slide today and yesterday, with the Casimir force also, you can have certain kind of scaling behavior where we can show that the Casimir pressure PC, it exhibits a scaling behavior which is expressed in this expression here. Now, first of all, what does it mean? Okay, first of all, remember the Casimir force or the Casimir pressure doesn't matter because the force and the pressure, they're just related, right? So it's a matter of the area only, which is constant. So I'm going to consider the pressure here. So the pressure now depends on L and temperature. If you look at the right-hand side, the first ratio here, that's dimensionless. Yeah. And why will it be dimensionless? Because the upstairs is basically energy and you are dividing it by the volume. So it's energy by volume. So it's once again going to be the pressure. So on both sides, it's basically pressure, which means that if I look at the scaling function here, theta is a dimensionless quantity, which is namely the scaling function. So it's a dimensionless scaling function, which depends on another dimensionless scaling variable, L over psi. Okay, let's not going to get into the further details. What to show you is the following. If you look at the first plot here, what I show here is the scaling property of this Casimir force as a function of the scaling variable, which is mentioned here. And you can show once again that different colors here correspond to different system sizes. Okay, so what you can show is that if I look at this Casimir force for different slit widths and I do a certain scaling analysis, data from different system sizes, they all fall on top of each other, which are the properties of scaling. Yeah. And in the inset here, what I show here is the same data on the semi-log scale. And you see it's straight line, which means that the scaling function, it's actually exponential in nature. Yeah, so it's an exponential decay. What's also interesting to see here is that this scaling function, if you, okay, so I don't really have it here, but if you could look at the scaling, if you look at the scaling function, you see that it's positive. Positive means that it's actually repulsive. And that is what is the prediction from analytical theory as well. If I look at the second plot here, this is for a symmetric wall. The point to note here is that the data that you get here, you see that the scaling function is positive, which means that it's a repulsive force. But if you look at the existing theory, which comes from renormalization group calculations, yeah, that predicts that the force is actually negative. So the question is, what happens suddenly? When you have the analytical theory, which is predicting that the force has to be negative or is attractive, the things which you are getting now is actually positive, which means it's repulsive. So what happened? What happens to the repulsive or positive thing? Why do they contradict with each other? And that leads to a very interesting and very important concept of ensemble equivalence. So the data that I show you here, first of all, they come from finite system sizes, and these are the results in the canonical ensemble. Whereas if you look at the predictions from analytical theory, those predictions are from the grand canonical ensemble. Okay, and when you have a system which is close to the critical temperature of a second order phase transition, and you are dealing with systems which are very finite in size, so these are not thermodynamically large systems at all. These are very finite systems which are close to the critical temperature. The ensemble equivalence need not hold, which means that the properties from the grand canonical ensemble and the canonical ensemble might be very different. And this thing which you see here, that the attractive force has now become repulsive, it's an effect of that thing, that when you have finite systems and you are close to the critical temperature, ensemble equivalence does not hold. Okay, so this is a very important concept in statistical mechanics, particularly in confined fluids, because remember, the moment you have confined fluids, your systems are no longer thermodynamically large. It's not infinity any longer. These are finite systems. So the idea of ensemble equivalence then becomes very important. Okay. All right. So yeah. So this is the idea which I wanted to give you. If you want to read more about the ensemble equivalence or the breakdown of ensemble equivalence, I strongly urge you to pick up any book on statistical mechanics. Yeah, Patria, Wang, Goldberg, whatever. Yeah, and you will find just read the chapter where it explains the ensemble equivalence, grand canonical, canonical ensemble. When are they going to be equivalent and all? Okay, so those are some very important concepts for confined fluids. Okay, so I think with that I will end the discussion, and let me just take up the questions which are there.